Okay, in this lecture, we are going to talk a special type of topological space, which are called connected space. We will be using separation of a topological space to study connected space. So let's first define a separation of a topological space, and then we will define connected space and we'll give some example. Okay, let's begin with the definition of a separation of topological space. Let's say X is a topological space. X is a topological space. X is a topological space. So here is the formal definition of a separation of this topological space. A separation of the topological space X is a pair U B of disjoint non-empty open subsets of X whose union is X. So this is the formal definition of a separation of a topological space. A separation of a topological space X is a pair U B of disjoint non-empty open subset of X whose union is X itself. So let's visualize this definition. Let's say we have a topological space X, and let's say we have two non-empty open set U and B in this topological space X, and this is our U and this is our B. Obviously these two are disjoint, and so U is non-empty open set in X, B is non-empty open set in X, and if we take their union, then it's gonna be X, and also this U and B are disjoint. That means if we take their intersection, then it's gonna be empty set. So if there exists such a pair of disjoint non-empty open set in X whose union is X itself, then that pair is called a separation of a topological space X. Let me add couple of note. Let's say if U and B, this pair is a separation of X, then they satisfy certain properties. Now let me list those properties here. Let's say if X equal to U union B is a separation of X. So this is how we write down a separation of X. That means if this union is if we say U union B is a separation of X, that means U and B are non-empty open set and they are also disjoint, and their union is obviously X. Then the first property, if U and B they form a separation of X, then neither u nor v contains a limit point of the other set. That means u does not contains a limit point of b, and also b does not contains a limit point of u. And that is obvious. You can see here. Let's say, okay, let me first write it down. Then u does not contain any limit point of b, and also b does not contain any limit point of u. And this is obvious. For example, let's say u contains a limit point of b. Let's say this x is a limit point of b. Then that's gonna be a contradiction, because if x is a limit point of b, every neighborhood of x should intersect b at some point other than x. Now u is an open set that contains x, so u itself a neighborhood of x, and u and b, they are disjoint, because u and b, they form the separation, so x cannot be a limit point of b, so that is a contradiction. So u does not contain any limit point of b. Second note here, so let me take the closure of u. Closure of u, that means if I take the closure of u, which is u union the set of its limit point, just let me remind you, u closure, which is u union u prime. So we have seen this in one of our lecture, in one of our previous lecture. So u closure is u union its set of limit point, and if we take the intersection of that guy with b, it has to be empty set. And this is obviously because we already know u and b, they are disjoint set, so their intersection is gonna be empty. And u prime, which is the set of limit point of u, since b does not contain the limit point of u, so u prime intersection b is also empty. That's why u closure intersection b is empty. Similarly, if we take the intersection of u with b closure, that's gonna be empty as well. So these are the two properties. They are going to be always true if u and b forms a separation of this topological space X. Okay, now here we gave I gave you a definition of separation of a topological space, and also a couple of properties related to separation of a topological space. Now next I'm gonna give you formal definition of connected set, and then we'll give you some example of separation, and then also connected space. So in fact, I'm gonna give you two definition of connected topological space. I mean, they are equivalent. Okay, let me give you the first definition. A topological space X is said to be connected. A topological space X is said to be connected if there does not exist a separation of X. If there is no separation of the topological space X, then that space is called connected space. It's called the connected space. But if there is a separation of X, then that space is not connected. And here is the alternative definition of a connected space. So alternative definition of connected space. In fact, the definition that I gave you here is, and the one that I'm going to give, they are equivalent definition. Okay, so let me give you the alternative definition. So a topological space, a topological space X is connected. X is connected if and only if and only if the only subsets of X, the only subset of X that are both open and closed in X are empty set and the whole set X itself. If the only both open and closed a set in a given topological space are empty set and the topological space X itself, then the topological space is connected. Okay, now let me give you a couple of definitions of separation of topological space and also example of connected space. Example number 1. Let's begin with an example of a separation of topological space. Let's say X is a topological space whose elements are A, B, C, and D with topology tau, empty set, the whole set, the singleton set A, singleton set B, two element set A, B, C, D, A, C, D, and B, C, and D. Okay, so we have a topological space X with this topology. Now there is a separation of X. So here let's take U is this set, this two element set AB. So U is obviously non-empty and is open because it's an element of a topology. And let's take B as the other two element set CD, so it is non-empty and is also open. Now we have two non-empty open set. Then if we take the union of U and B, so that is obviously A, B, C, D, which is X, and you can see there are no elements in common in U and B, so U intersection B is empty. Thus union B is a separation of X. Since there is a separation of X, so X is not connected. So X is not connected. So here I gave you one example of separation and also a topological space which is not connected. Example number 2. Let me give an example of a connected space. Let's say I have this 3-element set or topological space with topology tau. Let's say it is empty sets. The whole set, 2-element set A, B, and B, C, and then it's a B. So we have a topological space X with the topology tau. Then X is connected. This is because we cannot find two non-empty open set in X such that their union is X and then their intersection is empty set. So it's not possible to find those two sets here. You can see here it looks like this set and that set. So if we take their union is X but their intersection is not empty, so even their union is X but and they are open, non-empty, but their intersection is or they are not disjoint, so they cannot form a separation. So in fact we cannot find a separation of X. That's why X is a connected space. Example number 3. Now here any set with indiscrete topology, is connected. This is because if you look at the second definition of connected space, the second definition, it tells us that a topological space is connected if the only both open and closed sets are the empty sets and the whole set X. And if you have a indiscrete topology, so there are only two sets in the topology, or the topology has only two elements, which are empty set and the whole set. And since empty set and whole set both are open, so they are also closed. So that the only open and closed set in indiscrete topology are the empty set and the whole set X. That's why any set with indiscrete topology is connected. Example number 4. The real line are under the standard topology. Real line are under the standard topology. Is connected. This is again by the second definition of connected space. The real line R under the standard topology is connected. Because R and empty set are the only subsets which are both open and closed. You can see this one is easily. Let's say this is our real line, and under the standard topology, the open set in R, they are open interval. Okay, so they are the open interval. So these are the only open set in R. So if you have open interval, then that's the open set, and obviously open interval is not the closed, is not a closed set. So open interval, they cannot be the closed set, they are only the open set. That's why the only both open and closed set in R under the standard topologies under the standard topology are the empty set and the whole set R. That's why R is connected. And this is one of the popular example of connected space in topology. Now let me give you one more example. Any set with discrete topology, any set with the discrete topology is not connected. This is because in the discrete topology, every subset of the given set is open. That means all the singleton set of the given set are open. So it is easy to find a separation in the discrete topology for any set, because if we take those singleton set, just take the one of the singleton set as U, and the union of the remaining singleton set is a V. Since in topology the union of arbitrary union of open set is open, so B is going to be open, and obviously U, which is our first singleton set, that's gonna be open, and they are non-empty, and their intersection is obviously disjoint, and their union is the set X itself. So that is a separation. I mean, that is not the only separation. There could be the other separation, but topological space not to be connected is enough to find one separation. That's why any set with discrete topology is not connected. Okay, now here I gave you some example of connected space and also separates or the spaces which are not connected. So the next we're going to talk about the connectedness of a subspace of a topological space. So to describe the connectedness of a subspace in a topological space, we need a lemma. So let me give you this lemma without proof, and if you are interested in proof, you can take a look in Munker's book. Okay, let's say the lemma is, so here X is a topological space, X is a topological space, X is a topological space, and this lemma, it tells us that if Y is a subspace, if Y is a subspace of this topological space X, a separation of Y is a pair, a separation of Y, separation of the subspace Y is a pair of disjoint, it's a pair of disjoint non-empty sets A and B. The separation of Y is a pair of non-empty disjoint sets A and B whose union is Y, and neither of which contains a limit point of the other. The space or the subspace Y is connected if there exists no separation of Y. Okay, so this lemma describes the connectedness of a subspace of a topological space. Let's say Y is a subspace of a topological space. Then a separation of Y is a pair of disjoint non-empty sets A and B. So this A and B, these are like just the disjoint non-empty. These are just the disjoint non-empty sets in Y, and neither of which contains limit point of other. A does not contain the limit point of B, and B does not contain the limit point of A. Then this pair is called the disjoint. And this pair is called separation of Y. And if the space Y is connected, if there is no separation of Y exists, like for the topological space. But here we are dealing in terms of subspace. Okay, now let me give you the example of subspaces of given topological space which are not connected. Okay, example, let's call this one is example number 6. Let's say R is set of real number under the standard topology, and let's call Y, which is the union of these two half open interval in R, which is a subspace. It's a subspace of R. So what we have here is we have this real line here, and our U is, let's say this is center 0 of real line, and our U is it's this set and then union of this set. So it's just the union of these two sets. So in our Y, or in our subspace, we don't have 0. Then this space Y is not connected. This is a subspace of R. This is because now you can see here, if Y is not connected, then there should be a separation. Now this two set, there's -1 0 and then also 0 1. These two set, they form a separation of Y. This is because we are going to use this lemma. This lemma, it tells us that the separation of Y is a pair of disjoint non-empty sets. So obviously this one, this set, this interval and that interval, these are the two non-empty sets, and they are also disjoints because their intersection is empty, and then neither of them contains a limit point of the other one. The set of limit point for this one is the interval from -1 to 0, including 0, and the set of limit points for the other one is the interval from 0 to 1. And you can see here they have the common limit point 0. Okay, because the limit point for the first one is gonna be from here to here, for the second one is going to be from here to here. You can see 0 is their common limit point, but the 0 is not in the first set and also is not in the second one. That means none of them contains the limit point of the other one, so that these two interval they form a separation of this topological space Y. Okay, so you can write, let me just write down this the one that I just described here. Since each of the sets negative 1, 0 and 0, 1, 0, 1 is non-empty. 0 is non-empty, and then obviously they are disjoint, and then their union is Y, and they are also open in subspace topology, but they are not open in the standard topology, because they are open. I mean, we don't need here open. They are open because in subspace topology a set is going to be a subset of Y is going to be open if you take the intersection of Y with an open set in R, then it has to be that set. So obviously this guy is open, because if we take the intersection of Y with this interval, we're going to get this part. So this interval is open, that's why it's open. Each one is open in Y, but they are not open in R. Anyway, we don't need the open, since each of the sets negative 1, 0 and 0, 1 is non-empty, and neither of them contains a limit point of other. So they form a separation of Y. If they form, since we found a separation of Y, thus we can say that Y is not connected. So Y is not connected. Okay. Example number 7. Let's say R is the set of real number with the standard topology or order topology. They are the same thing. And let's say Q, which is the set of real number, is a subspace of R. Now here this Q, which is the set of real rational number, is not connected. This is because to show Q is not connected, now you can take a look here. This is our real line, negative infinity, positive infinity, and like I said earlier, Q is not connected. If Q is not connected, then we need to find a separation of Q. We need to find at least one separation of Q. To find the separation of Q, let's say let's consider two real number, P and Q are in Q with, let's say, P is less than Q. Because if you have two rational number or real number, they are always comparable. Okay, let's say this is my P and this one is our Q, and the uppercase Q. We are trying to find a separation here. Okay, since P and Q, these are the two real rational number, so between two rational number, always you can find an irrational number. Let's call that irrational number is R. Suppose P and Q are in Q with P is less than Q, then one can find an irrational number R such that P is less than R is less than Q. Okay, so here R is a irrational number. Okay, now here what you're going to do is, now we have this two interval. So obviously from negative infinity to R, so this is an open set in standard topology, and we have other one this side. This is another open set in R. Since we are considering a subspace topology in Q, and we are trying to find a separation of Q. Okay, so to find the separation, we going to use the original definition of separation. So what you're going to do is, we're going to find two non-empty open set in Q in which are disjoint, and their union is Q. Okay, for that one, let me take the intersection of Q with this first open interval in R. So in subspace topology, so if you take the intersection of Q with the open set in the standard topology, or the open set in the topology in our original topological space, then this intersection is gonna be always open. Okay, so this one let's define U like this, and B is in the same manner, but you take the intersection of Q with the other open set from R to infinity. These are open, and obviously they are non-empty because the first one has P and the second one has Q. P and Q both are like these are the rational numbers. So here in this intersection you have at least P, and here at least Q. These are open, non-empty, and then obviously you can see they are disjoint because the first one, all the rational number on this side, and the other one, second one, B is the set of all the rational number on the other side. So they are non-empty, disjoint. There are open, non-empty, disjoint sets in Q under the subspace topology, and also Q is the union of these two, because that intersection U or this set U is the set of all rational number on this side, on that side, and B is the set of all rational number on the other side, and if we take their union, that's gonna be the set of all rational number. And also Q is the union of U and B. So thus U union B is a separation of Q. Since we found a separation of Q, so Q is not connected. Okay, so here this is another popular example of a space which is not connected. All right, so far I give you multiple example of a space which are not connected. But the question is, how can we construct connected space? Okay, because we have seen many examples of not connected space, but if you need connected space, or if you want connected space, question is, how can we construct such a connected space? So in order to construct the connected space, I'm gonna give you a few lemmas and theorem without proof. Those lemmas and theorem, they tell us how to construct a connected space using the other connected space. Okay, so let's begin with the first lemma. So again, I'm not going to give proof of this lemma and theorem. If you are interested, you can take a look in Munker's book. Okay, so here is our first lemma. If the sets C and D form a separation of X. X is a topological space, and we have a topological space, and C and D form a separation of X. That means C and D are non-empty open set and which are disjoint, and their union is X. And if Y is a connected subspace, and if Y is a connected subspace of X, then Y lies entirely within C or D. Okay, let me let's visualize this lemma. So we have a topological space X, and the separation of this topological space, we have this separation. This side is C and this side is D, and C and D, these are non-empty disjoint open set, and their union is X. And if Y is a connected, let's say this Y is a connected subspace of X, then Y, it has to be entirely within C or entirely within D. It cannot be the part of both C and D. It has to be either within C or within D. It cannot be like this one. And that makes sense here, because if it is like this one, if let's say Y is the part, some part of Y is in C and some part of Y is in D, then Y may not be connected, or Y is not going to be connected, because this portion, let's take this portion and then the other portion. So this the portion that I have highlighted in red and then blue, they form a separation of Y, and that's gonna be contradiction for Y is connected. So that's why this Y, it has to lie entirely either in C or in D. It cannot be the part of both C and D. That's the statement of this lemma. Okay, all right. Now the next theorem. So this theorem will tells us how to construct a new connected space using the other connected space. And here is the statement. Just the statement. We are not going to present proof here. If you are interested in proof, you can take a look in Munker's book. The union of a collection of connected subspaces, of X that have a point in common, is connected. Okay, so this theorem, it tells us that the arbitrary union of the connected space is going to be connected if all the connected space has a point in common. Okay. Okay. Now there are two more theorem. I'm going to give you here, and they will also tell us how to construct a new connected space from the other connected space. This theorem, it tells us that the image, basically this theorem, it gives us the relation between continuous function and the connected space. The image of a connected the image of connected space under a continuous function. So we have learned continuous function in one of our previous lecture. So the image of connected space under a continuous map or function is connected. So here we can use connected space and the continuous function to construct new connected space. Again, I'm going to skip the proof of this theorem here. And here is one more theorem. And this theorem also tells us how to construct the new connected space from other connected space using Cartesian product. And here is the statement: a finite Cartesian product of connected spaces is connected. So if we have connected space, then we can take their Cartesian product. If we have finite number of connected space, and we can take their Cartesian product and construct the new connected space. Let me give you example of connected space using this last theorem. We already know R is connected in standard topology. So R2 is connected because R2 is the Cartesian product of R with itself. So as I said before, R is a connected space in the standard topology. So R2 is also connected in the standard topology, or standard topology in R2 is same as the product topology. So R2 is connected. It's being a Cartesian product, of the connected space R with itself. If we take the Cartesian product of R with itself, we're going to get R2. Since R is a connected space in the standard topology, so R2, which is the R cross R, is connected in the standard topology, or in R2 standard topology is same as the product topology.